Okay, now we are in week 10. Week 12 will be your test. Week 12, week 13 will be your test 2. Week 12, please submit your lab report. Week 12, there's 2 more weeks for your lab report. Assignment, please submit by week 13. Okay, now chapter 6, we start to go into rigid body. We have done in chapter 5, we did done the rigid body equation to transform the chapter 1 parameter. Okay. Now recall what is your chapter 1 parameter. Basically, it's just a transformation, transfer what you learned in chapter 1 as U, V, A, T, all right, in chapter 1 and all the 3 Newton equation. All right. And then chapter 6, chapter 5, what you need to do is, because chapter 5 you deal with rigid body. Rigid body, it will try to rotate omega and alpha. Okay, now in chapter 5, what you need to do is transfer S to theta, S to R, U or V velocity into angular velocity, which is omega. Acceleration will be in alpha, right? I mean all this term all this term, and of course there will be equation link velocity to omega in chapter 5. So V equal to omega R. Alpha you have 2, because chapter 5 you have rotation. Rotation, your body will go through circular motion. Circular motion, you have normal and tangent direction. So your acceleration will have AN and AT, right? So your AT will be alpha R. Again, tangent is velocity, is same like velocity direction. So velocity direction you link with alpha. R, AN is omega square R, right? So these are all the equations that you need to memorize. And when you do the transformation here, is when your alpha is constant, then you substitute the 3 Newton equation with all these parameters. Okay, so these are the thing that you need to be take note. Okay, now in chapter 6, I'll go very fast. Chapter 6, I'll go very, very fast. So all the examples, sometimes I will just jump and you do it as your homework. All right. Now, chapter 6 will be linked with chapter 2. Chapter 2 will link with all the force will equal to MA. Here, we also do the same. We will link with MA. But today, in chapter 6, we will look at moment of inertia. Okay, moment of inertia. So moment of inertia means you consider the body mass already. Body mass will give you inertia. In particles, in chapter 2, you don't consider the inertia effect. But when it comes to chapter 6, rigid body, you will consider the inertial effect. Inertial effect. Okay. Then we'll use F equal to ma for 3 motion: translation, rotation, and general plane. This is from the chapter 5. Okay, rigid body you have 3 motion. Translation, with this translation moving without orientation change. Okay, so it can be linear, it can be collinear translation, then rotation like that. Okay, rotation is a change of orientation. Then combine, it become general plane motion. Okay. Okay, let's watch this video. Some of you don't know what is flywheel because your test 2 or your final exam, you might see what is free will question. So this is a very old car. Free will is this component, right? So old machine, they will use initial mass initial to start everything. So when you try to rotate something, the object will remain its own position. So when you turn something, you continue to turn because of inertia. So this is how 1890s, when they invented automotive, they use the flywheel, this component, to keep the piston moving. So this is linear motion. Now we go into a little bit on theory. So let's say you have a rigid body, and we focus on point with the mass, because now we're in the rigid body. Yeah? So when there is a point with a mass, it become a, and you will try to rotate. There is a motion, right, with the R. So we try to give an equation for this inertia, right? So inertia give you by this equation, right? So if you learn your statics, you learn about the Ixx, Iyy, Izz in your statics, right? Or in your max chapter also, you'll find the central of inertia for the object. For finite element analysis, also you need to know how to find Ixx, Iyy, Izz. So for chapter 6, initial is the main focus. So I equal to integration of I square dm. R is the radius or the distance from the axis, body axis, R, and it's 90 degree from the axis itself to the focus of your mass. This case is a very small mass here. Right? So it's the integration. So R here is moment of arm. It's a moment of arm. But as long as you understand that this R is from the reference axis. Okay. Okay. And for rigid body, we will start to focus on center of mass. Center of mass, which is G. It is G on the body. Right. So center of gravity will always go through this z-axis here. Center of gravity. Okay. Now, moment of inertia is always positive quantity. It always give you positive. No matter it is positive R or negative R, because when you square it, you still get positive number. Why there is a negative number is when your R go opposite direction. So this is a R positive direction which go outside from the axis. So when the R move into the axis, then it will become negative. Okay? But here, if you want to calculate inertia, you square it, you still get positive number. So common unit for inertia for chapter 6, you need to be familiar. M is a mass is kilogram, R is in meter, so meter you square, you get meter square. So unit for inertia will be kilogram meter square. So this is the first equation for today. Then we can split the M by your physics understanding, how to find mass with the density and volume. Mass will equal to density multiplied by volume, right? So same here. Okay. So why we need to learn how to develop the equation? Because in most of the engineering problems, you don't know the mass of that object, but once you determine or you find out the type of material, then you know the density, right? So from the handbook or any encyclopedia, material encyclopedia, once you identify the material, you will have the range of the density. So by the latest technologies, you can do scanning, you can use photo, you can use infrared, you can find the volume. Okay. So when you have this density and volume, you can find inertia for that body. Okay. So we try to link the M, we split into density and volume. Okay. So you know that density doesn't change, it's a constant value. So we cannot d-rho, we cannot change the rho, but we can change volume. So this is a constant value, this is dV. So that's why in the equation, dm become rho dV. Then we slowly, what I need to highlight here, your integration just now is dm with its mass. Now, when you develop dm into rho dV, you integrate volume and no longer mass. Okay. So you know that rho is a constant, so you can pull your rho into the front. Okay. So you change from a simple inertial equation into rho r dV. So you have three parameter: density, distance from axis, and volume. Okay. So if we have one body in this domain or in this bullet shape, so you can calculate the inertia for this one. Okay. So you know volume, how to find volume in the three-dimensional, dy, dx, dy, dz, then you find volume. Okay. That you learn in your mathematics, how to find volume in three-dimensional. You do triple integration. This is what you learn in Max 2 or Calculus 2. You do triple integration. This is x, this is y, this is z. Okay, so you integrate inner, then once you've done this one, you integrate out, then create the z. Okay, so again, this is a homework. We assume you already know how to do triple integration. Okay, so first we look at shell element. There are two methods that you can calculate volume. We introduce you the first method, which is called shell element. Means we will use this shell to define the volume by the changes of y dy parameter. Okay. So we choose thickness as into our. So to find volume of this one, so if you use shell is like a drum shape. All right. So how you find volume of drum shape? You take the area or the circumference of this circumference, then you multiply by thickness, then you multiply by the height. Okay. Okay. So dV equal to 2 pi y, 2 pi y multiplied by dy and dz. So this is how you find your shell volume. Okay. There are First method is shell element. Shell element, you use volume, and then there's a change of dy here. The change of dy. This is a shell method. dv equal to 2 pi r. You can use r or z, then multiply z dr. Okay, in this case, we use x, y, z to represent the axis. So this is shell. So 2 pi r is this radius, and then you multiply by the dy, you get the area of the circumference circle. Then you multiply by z, you get volume. Okay. Okay, can you understand? 2 pi y dy is this area. This area multiplied by height, you get volume. Okay, second method to find volume is use this element. Just now is shell. This is this. This is the change of Ez. Okay, the equation will be 2 pi r dz. Okay, so these are the second method. So dv equal to pi r square or pi y square multiplied by dz. What is the difference between these two methods? Okay, so you cannot use for determine the moment inertia z of the body about x-axis directly. So if you use this element, you cannot find moment of inertia directly for the iz. Why? If you compare side by side, this one will give you more accurate data compared to this element. This element, you straight away you fix your y already, fix your radius already. Okay. Again, this one you need to be careful when you can use, when you cannot use. Okay. Because why? In the rigid body, you don't have a cylinder shape. You have, this one is a bullet shape. So when bullet shape, if you use this method, you won't get the accurate inertia. Okay. So compared to shell element, shell element, because the radius is changing, so you can get more accurate volume compared to the second method. Okay. All right. Now in the chapter 6, it's always you need to determine the moment of inertia about the z-axis, then integrate the results. So this is the steps for chapter 6. So when you see chapter 6 question, the first step is to find moment of inertia. Okay, this is the equation we expect in your answer, and in your test one you already know how we mark your test final exam. You do not write general equation. Sorry, there's no marks for your answer, right? So you have to show understanding of this. You're actually using this method, right? So you have to show that, okay, you actually understand. I'm using what method to solve this question. If you just substitute value, then sorry lah. So in this class, there are one student that actually do not write general equation, and that's one, but didn't get the marks for the answer. Okay, so just take note lah. All right, now that's a very simple exercise. So example 1 asks you to find moment of inertia of the cylinder below about z-axis, density of the material. Sorry, this one should be rho and not r. It should be rho is constant. So there are two methods. You can use shell or this method, but this one is a cylinder. So cylinder, you can use that method. So how do you use a triple integration? Right, I equal to r square dm, or I square equal to rho r square dv. How to find v? Triple integration of your dy dx dz. So in this case, in the shell element, you fix axis Z, and then you identify where is your X, where is your Y. In this case, your X and Y is the same. So, and this one, the question give you is start from the center of mass, which is O there. Although this example, later in chapter 6, you will start to see question give you the center of mass, or ask you to find where is the center of mass. So in this case, at the center here, and R, dr, this is steps for cell element because you're changing your Y direction or your R direction. Okay. So you start to find your volume. How to find volume for this one? How to find volume? dV equal to what? Equal to what? 2 pi R multiply dr. You get the area of this region. Then you multiply by the Z. Okay. Okay. So here you have total. The height is from here to here. So total H. Accurate calculation is there are two volume here. One is above the O, one is below the O. But this is a very simple example. So we take the H divided by 2 plus H divided by 2, you get H. More proper steps in mathematics, you know that this is O at the center, so you need to calculate above and below. There are two calculation volume there. So the mass will be rho dV. So you substitute rho equal to 2 pi R drh. Okay, shell is that you calculate the circumference, then you multiply by the change of radius, you get the very, very small changes of area. Then you multiply by the H, you get volume. This is a shell method. Then you put inside the inertial equation I equal to integrate R squared dm. Then you get the answer. Right? This is the full answer for the first example 1. Okay. Right. Then you do integration. Okay. You do integration. So these are the steps of your integration. Okay. You know that is dr. Why there's a square cube there? Because 2 by r and r square here, you get r 3r, 3 multiply 3, right? Exponential 3. dr, what you get? Only this section, what do you get? R power 4 divided by 4. Once you integrate 4, and you put inside here, so 2 over 4, you will get half. Okay. Okay, so those that you still weak in integration, please polish up. If you're weak in integration, very high chances I'll see you again in next semester. Okay. So you do the integration, you'll get half rho pi h r over 4. Okay. Right. So can you put in terms of mass? Can you put this one in terms of mass? What is mass? This one? Mass equal to rho v. So what is your v in this case? Pi r squared h, right? How you find mass or volume? Pi r squared divided by square h, you get your mass. Get your volume. Okay. So your mass equal to rho pi r square h. Can you change into this one into mass? Iz equal to how many mass? How many m? How many m? You understand what I'm asking, right? So I equal to how many m? We want to put in terms of mass. This one changed to m. I write on the whiteboard there already. One m equal to what? What is m? M is rho pi r square h. So this one change into what? How many m? You understand what I'm asking, right? So what is the answer for how many m? You understand what I'm asking, right? From this example one, your I equal to rho pi hr power 4 divided by 2. You have your m already. Equal to how many m? You understand what I'm asking, right? R square over 2 or half mr square. Okay. So the answer is half mr squared. Okay, again, don't worry about the derivation because in chapter 6, you will see a reference, a table in your appendix. You will see a reference chart or reference table when it comes to test 2 or final exam. You just need to refer to the correct shape. And I just introduced you this morning how we get the first one. There are lots of different shape lah. But again, for chapter 6, you'll be provided appendix in your assessment. Okay, you only need to know where is your z-axis, where is your y, where is your z. Because in the table, you'll be given I, z, z, I, x, x, I, y, y. You read the wrong one, you get the wrong one. Or you can derive from like what you see on the example 1. But it will take you like another 5 minutes to reach the one. Or you can just maybe 2 seconds from the chart. Okay. Example 2, we'll use this element. So example 2, you have a cone. And this cone surface change given by equation y square equal x. The height is m. The bottom base is 1 meter. Density is 3,000 kilometer per meter cube. Determine the moment of inertia for this axis or for this object. So now we use this element. All right. Just now we use shell, and now we use this element. So we use this element means the change of dy. Okay. Why we use this method? Because now your y is your height. Your height is linked to x. That's why we can use this element. Just now we are looking at x, y, and z. Now your axis change already. Now your axis is y and x only. Okay. So what is changing is your dy. So by using the method, how to find the m, rho dv, how to find volume, you find the area, multiply by the h. So pi r square multiplied by dy, you get your dv. Then you want to integrate. What is changing? The y is changing. So your dy. That's why you force our equation development here into dy. Those y is changing. Okay. So here, you put everything in, all right? You will find that it's actually, you can simplify. I equal to integrate r dm. You pull the same thing, you do the same thing. This, you know that you dm equal to this one. Then you put inside the I equation, right? Just now your I is this one, right? Okay, your I, you try to put into this equation. You put this whole thing inside here, you do integration, still the same steps like what you see in the example number one, right? So you substitute, you get this one, right? You substitute the density there, you get the answer. Okay. Okay. So this substitution, why? Because this one you have dy there, all right? You have dy there, so you integrate. You actually integrate with your y. So you need to substitute, change your x into y point. So this one, x equal to how many y? You substitute whole equation, you only have y parameter. Then you do the integration. Okay. So this is how you do. Second one, we introduce you a parallel axis theorem. Parallel axis theorem, as you see on the screen here, you have z and z prime. Again, when you see z without the prime is your reference axis, which is a permanent axis that do not move. Then this object moving, so you move in the refer to the object, we'll use prime or comma. So z comma, x comma, y comma is the one that stick to the bodies. Okay, so this one you learn in the last part of the chapter 5. You start to see x comma, y comma, z comma. Then we introduce you more in chapter 6. So you can see here the center of gravity G, and then the M here. So you have R, you have the R here, and then A to G, there's a distance D, and there's a change of R prime. So R prime, dy, dx. Okay. So if the moment of inertial body is about axis pass through, moment of inertia pass through, okay, pass through the body mass of center, G here. Then moment inertia about any other parallel axis can be determined using this theorem. Okay, meaning this we are using parallel axis, right? So we are using this parallel axis. Okay. So again, D must be perpendicular, must be 90 degree to the two lines here. Okay. So again, this one is you read, you use Pythagorean theory, R square equal to D. This distance, this is 90 degree. This is a triangle. So R square equal to this distance square plus this distance square. Okay. So we want to express in z-axis. So I equal to R square dm. So what is your R? Is this terms. So R square is this square equal to this square plus this square. So we want to use this distance and R, y comma. So we change the R into this term from this diagram. Okay. Then you do integrate. Okay. You expand this one, you do rearrangement. you have two components. You can group the result of this integration into two components. One is prime component or comma component, x component, y component, and another one with the dx prime dm from here lah. So this one you can work it out during your revision time. Okay, so there are three actually. There are three. There's one more with the d square. Okay, so what else? Okay, so what are the three components if you integrate this one? There are three components. Okay, so the first component, x comma square plus y comma square dm. This is represent the center of gravity inertia. This is what you learn in your statics, in your static chapter. This one, the second one, 2d dm, x prime dm. This one, because the x-axis pass through the body mass of center, there is no inertia. Then this one represent the total mass of the bodies, dm. Okay. So you simplify the equation. For chapter 6, this is the first one. Then second one will be I equal to Ig plus dm, and d squared. Okay. So moment inertia, it depends on where you find. Okay. Now, what is the difference between the result that we see from the general equation is that now you have two components. Ig is from the center of mass. This is from a distance or from the observer. There are two components. Okay. So if your reference point, let's say I have a body, write something on the whiteboard. If I want to calculate moment of inertia in G, I don't have this component. This one is your Ig equal to I. Because there's no D there. There's no D. There's no reference here. Your A point is in the G now. Yeah. So many students confused when they come to this equation. I equal to Ig plus md square. They don't know when to use this one. Okay. Is you use this one, you look at the reference point. So when the question gives you a reference point or observer point, then there is a D distance. If the question asks you about the body, the center of mass, G, at the G central of mass point, then you don't need this one. The D is 0 because you already move your focus point into A to G already. You need to read carefully the question. The question either asks you from where. If the question asks you from the central of mass, straight away calculate this Ig. This one you read from the table. Okay. All right. Okay. Now, since we start to look into rigid body, when you have a case called composite body, means you combine with the loss of bodies. All right. So then you find the sum of the inertia. Like you find the inertia for your head, for your two arms, your bodies, and your two legs. You sum or one. Your head have one Ig, one moment inertia. Your two arms also have different moment inertia. Your body also have, your leg also have, depending on the reference. So this one only have when I refer my head to this point here, then I have this equation. Okay? When I refer to this corner to my head, then I have my D, I have the D to my head. Right? If my reference point from my head to my body, then for my head, I don't have this one. But for my body, I have the D. Yeah? It depends on where you refer to. Okay, it means your air point here. So during composite, you need to be careful where you put your reference point, your observer point. So if you composite, then you need to be careful. When you composite, usually the starting point don't have the MD square. Because usually you put the A same as this one, and then refer to individual bodies. Okay, so again, IG refer to appendix. This one already in the canvas, and get familiar with these two table. So on the left hand side is area. This one, you see this one in your statics, or max 2 or max 3 sometimes. You still remember IXX, IYY? You learn your SPM or SPPM. This is a 2D. But in rigid body, you look at this table. Just now, we proved in example 1, I equal to half m r square, right? So just now, the cylinder just now, we refer to the first one. And if the second one, you use this one, and you use this one and this one, referring to which case you have. In this case, in the table, you see IXX, IYY, IZZ. How you know which one to choose? It depends which axis you are referring to. For example, just now, the question give you z-axis here. So you are reading IZZ equal to half mr square. Where is your r? Refer to this table. You already given the r here. So just read where does the r form. Okay. Sometimes the question will give you this axis. So you just read IXX, this equation. Just copy this equation. Okay. Although this one the numbers is very small, but in the exam you see very clearly. All right. So important is you know where to look for. So for example, plate. You have X, Y, and Z also. You're sure there's a G point there. There is the central of mass point there. Okay. So you depends on where is your axis. Right? If you look from here, then you use x-axis. You look from here, you use y-axis. You look from the top, you use z-axis. Okay, same with this one, the rod. Just now our rod have half, right? Half h, half h. So same. If you combine this one and this one, you still get arrive at half mr square. Okay, so here you have a few lah. Okay, get familiar with this table. So now we show you how to use this table. All right. Okay. You are given this object. We start to go into more and more complex shape already. But again, it's like playing Lego bricks. You do subtraction or addition. Means you can combine all this shape, become one complex body. It's like playing Lego or playing laser cut or doing welding. So if you see this object, given you density, thickness, determine moment of inertia. Again, how do you know is a chapter 6 question compared to other chapter? From chapter 1 to chapter 5, and then go into chapter 6. You will see density. Other chapter don't have density one. When you see density, sure confirm you need this equation and this equation. You need to calculate the volume, the mass, not volume, the mass. Mass, you need density. Okay. So if you look at this one, this object given you the R, thickness, and so on. This basically, when you want to solve this one, refer to this table. is actually two circles. You do subtraction, right? You have gone through the technical drawing, right? Technical drawing, you know subtraction, right? Or you use a three-dimensional 3D software. When you draw something, you subtract the another object, you get this object, right? So how you do? This actually is a composite parts. We call it composite part. It consists of two. One is the big area, this which is the radius of 250 mm, and another one, this is 152 mm. So what you do, you calculate two moment of inertia, you take the big one minus the small one. Yeah, so it's this one. The rest is just the steps that I showed you just now. Important is you know the approach to solve moment of inertia. Now we talk about composite body. Okay, so again, you don't need to worry how to find this one, because this one already in the table already. You just need to read the correct axis. Okay, now refer to table IG. Okay, this is table IG. The formula here is IG plus MD squared. There's no D there. Straight away on the center of gravity. There's no D, D0. D0 here. So refer to table G. I enlarge the circular disc. So here you have IXX, IYY, IZZ, IZZ prime or comma. Where is IZZ comma? Here. This is the center of gravity. This is Z. This is IZZ. It depends on the question, where is the location of the interest point. In this case, there's no interest point, but it's a very general cases. The G is at the center. Where is your Z? This is your Z. This question very direct. You read from this one. Not here. Okay. Okay. So we're choosing the ZZ and not XX and not YY. Okay. I hope you understand. You solve it by looking at where you look at the object. For example, this example 3, how you do this subtraction? You look from above, right? You look from above and then you subtract big one, small one from the big one, right? You look from above. So when you look above, you're looking at Z-axis from above. So you use IZZ and not from X, not from Y. If you use X and Y, means you look at the side of the body. Yeah. So don't confuse with the 3 axis there. Yeah. So this one, I hope you understand. Once I understand this one, chapter 6 will be very easy for you. Okay. Now with this one, only need to substitute the value lah. Okay. So this one you use for big one. This one you use for a small one. You have the R already. Just don't substitute the wrong one. Okay. R, the first one, second one, you minus. Where is the M? How to find the M? M, you're given density already. You know how to calculate volume. For big one and small one, you have the thickness here. Right? Volume equal to pi r square multiplied by thickness, then multiply by density. You get the M. Yeah. Okay, I go very fast here. So here, again, you know that you have this Ig equal to md square. Okay, I equal to md square. Okay, so here, so I just use the equation. So the complete one is half md square, mr square. This one from the chart plus md square. This one we don't have d. So you substitute the value, you get this one. Second one also same. I name it as hole. You do the same also. You'll get this one. Again, the D is 0. So in your solution, you just use arrow, then write 0. Go use arrow, write 0. There's no D there. Okay. Okay. Another this one is what? Example 3. Okay. Okay. Now we use the sorry. Okay. So the answer here, you see the substitution, the answer on the screen here. I label as O. So when your D is 0 when you look at G. So if the question asks you where is the moment inertia at the point O, then there's a D already. Then there's D already. So these slides, you see there's a D bracket O. It means it refers to O. Just now I asked you to cancel the D because you're looking at G. But if the question asks you what is the moment inertia at O, then you need to put in the complete equation with there is a D there. D from where? D from the object, the observer to the center of mass, or to the object. So here, the first one, the D here is 250 mm, because we're looking at the point O. Same with the hole, we're looking at the point O here. Okay. Okay. So when you do the substitution, you get that one. Although there's a plus here, actually it's a minus. Plus here, because we are doing a composite object, we always add all the moment of inertia together. By this case, we do subtraction. Okay. We can continue. Then we dismiss a little bit early. Okay. Now, this case also the same. I'll go very fast in example number 4, but try to observe the approach. Try to observe the approach. Now we have a pendulum case. This one is a composite object. Means you need to do different eye for this one. So there's a I-beam here, or there's a pendulum here, suspend at pin O. So you know when there's a pin O, then there's a D there. There's a reference point there already. So it consists of two thin rod OA have a mass. Or in this case, there is no density, but it straight away give you the mass. Then BC have a mass. Determine moment inertia about an axis passing through. There are two cases here. One is ask you to pass through point O. One is ask you to pass through the center of gravity here. Okay, there are two different moments of inertia. This question asks you to look at two different locations. One is O, one is G. Okay, I show you. So again, we still do not run away from this equation. I equal to Ig plus Md squared. Okay, D is from your reference point. D is from the reference point. Right, so by using table, part A, part B. So part A, we look at the first one. This one, by using table, you're actually looking at rod. This one. You're looking at rod. So where do you looking at? You're using Ixx, Iyy, Ix prime, or Iz prime. If you want to solve point O, where's your point O? Here. Where's your object? You look at the object here. You do not ask you G. The question do not ask you G. So don't look here. So when you do not look here, ignore X, ignore Y, ignore Z already. He asks you from one point here, which is here. This point, yeah? Okay. So the mode is always here, blah, 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 plus 3.0. So you're using X, comma, Y, comma. Yeah? You're using this one because you're looking at O. The question part 1A is O. But remember the orientation. The orientation go down. This one go up. Okay. So you read from here. 1/3 ml square. Where is your L? You measure. This is L. From here to here is L. Okay. Now, here to here is L. Sorry. Here to here is L. Your L is 2. Okay. The rest you just substitute. Okay. So we're interested your inertia from O. Okay. This is for the first part. Why there's no MD there? Why there's no D there? Because you straight away you read from the table. The value you read from table, there's no D there. Although you change the interest point here. Understand? Okay. You see, part 1 we do not have MD squared. Why? You read from this table. You read from this table, and you do not your D do not your interest point. You read from this one. You do not run outside this object. You still read from all this point here. So you are actually getting the IG value. Understand? Yeah. Okay. So again, so for the first part, the value that we read from here is IG. Okay. My question here is why we do not put in MD square for the first object. Because you're reading from O here. You're reading from O. Here you straight away find the O already. The D is 0. Your O point is here. Your O point is here. So there's no D there. Understand? Try to clear this one. If not, then you cannot follow the rest one. This one you can derive from the equation, but straight away you read from this table. Straight away read from this table, find this one. It's a rod. You don't need to worry how to derive the equation. You only need to know how to find which one is the correct one to use. Yeah. So because the first case is from O, from this point, the D is here already. So 0. Okay. Try to clear this one. Okay. So again, anyone you don't understand why we use this one? You don't understand why we use X comma Y comma. Yeah. And there's no D there because we are referring to this point. The D is 0. Okay. So your OA component from this point is get this one. You just substitute with 0D. But you don't forget there's one more part here. This is a composite things. So now, okay. Wait, this one is from, okay. You see, but if you want to you want to use this formula with the D also can. You can use this IXX also. but you're referring to G point. If you use this part, you actually your reference point is here. There's a D already. If you use the second method that I show on the screen here, that you move your O point into this point, into the center, then you have your MD already. But again, you arrive at the same equation. You arrive at the same equation after you substitute 1/12 ml square plus md square. Where is your D? With it here. Or here, your Y. So that's why there are two methods. It depends on which one you like, but you arrive at the same answer. Understand or not? There's two different methods. Both arrive at the same. Okay. Now the first one is straight away from the answer, the question point from O. You straight away read from here. If you want to make yourself suffer, can you move your interest point to G? When you move interest point to G, so you are looking at X and Y, but the question asks you from O. So there's a D already. There's a distance from the question already. So there's a D there. So the question is IG. If you use this one, this one is this one plus MD square. Where is your D? This is the distance of D. So you need to substitute this L over square here, or you use here. This is the length you substitute here over here. You still arrive at this equation at the end. Yeah. Try to understand, like, can I use that? Can I use that? Both approach arrive at the same IG. Okay. And try to ask yourself, do I understand when do I need to use MD, when I don't need to use MD? It depends on your reference point. Okay, this is the first method. The one you see on the screen here is first method. Straight away, refer side by side. Where is the scenario? Your D will be 0. If you want to make your life suffer, you use second method. You read from the IG, then plus MD square, you need to calculate the D here. This one. IZZ is from, there's no IZZ. There's no IZZ. Here, you only have one Z axis. IZZ, you shift the thing already. So it's not possible to find another G. You shift outside. No moment of inertia. There's no change of Z. Okay. So that's why IZZ is 0. There's no Z comma here. Okay. Means you see this one, X comma Y comma here is the shifting point, a moving point. So you cannot move your axis. You cannot move the body of the axis of your body. You cannot move outside. Cannot. Right? Okay. So this is the second method. Okay. Again, both arrive at the same answer. You'll get for the first component A here, or O component OA is 16 kilogram meter square. Now you do the BC. BC also rod. BC also rod. But now, where is your axis? Your rod is here. Your connecting point is here. Your rod is here, but your connecting point is here. Where is your O? The O will pass through the center of the body. So you are using IXX, IYY at the center of this body. Okay, BC have one center of gravity here. Okay, that's why for the second part, BC body, you are actually using Ig plus md square, your Ig read from here because you are reading from the center of the body. You're reading from the center of the body, G here. But there's a D there. What is your D? Here to here. There's an observer point to the body. This is your D. Your D is O to the center of gravity here, which is 2 meters. Yeah. Okay. So you substitute the value, you'll get for BC 37.8 something kilogram meter square. Then you combine the first one and the second one. Okay. You combine two, you get 57.7. Okay, this is from part A. You refer to point O. Now for B, see if you understand or not this equation. I equal to Ig plus md square. Now we shift our focus point to this point. Okay, still the same two body. So at first, when you solve this question, you write Ig equal to IOA bracket G plus bracket IBC bracket G. Means your focus point is now changed to G. Then you start to look at the scenario. Okay. Now, see if you're able to imagine the steps. You know that you need to combine moment inertia of first body, second body. Now the second part is the center of gravity G here. So for the first part, you need to find the Y bar or the average Y there. How to find Y bar? This one you learn in your statics already. Y bar equal to sum of mass. Y bar equal to all the Y bar small m. So how to find? So what is your Y bar? Y bar is the whole thing average distance from the reference point to the center of gravity G here. Okay, have you seen this one before? No. Never. Okay. So this one actually is one of the mathematics chapter. So let's say you have A, B, C. So how to find the Y bar for this object? Okay. So let's say I give you the mass 1, mass 2, mass 3. Okay. So let's say this is a center point for Y and this is your datum. Okay, this is your datum. So this is your first Y bar 1. So how to find Y bar? So Y bar equal to the sum of mass of total body equal to the individual summation of these three body. So the first one is what? Y1 bar multiplied by the mass of A plus second one, you go to here. From datum to here is Y2. So Y2MB plus this one. From datum, this is Y3. So Y3MC. You find this one, then you move this one to here. You divide, you get this equation. Okay. So okay, this is to find the average distance. Average distance. So the one that I already write on the whiteboard there. So if you want to know more about this one, you can go Google how to find the X bar, Y bar of the composite body. Y1. Y1 is This is 2. Okay. So Y1 is this member, right? This member. Forget about G. If you're given a body, this is your datum. This is your body. Where's your center of length here? It's at the center. It's always at the center one. The center of gravity or center of mass, always at the center of your bodies, right? So where is your G? G is half of the length. You're always at the half. So this one, let's say 10 meter. This one will be 5. You're always half of. So here, why you get 1? Because the total length of OA is 2. O to A is 2. Divide by half, you'll get 1. Then where is BC? BC is from here to here. The datum is here. To this location is 2. Okay. Yeah. It's always at the center of that line there. Okay. Then the mass is 12. This is 9. You get Y bar. Okay, so this is also one of the careless mistakes, or you will jam at these steps. Clear? Okay, good. So the moment of inertia Ig may be defined from the same manner as IO. So IO equal to Ig plus MD square. Okay, so you know that your IO just now is 57.7. You want to find your Ig for this first object is MD square. M is 21. Okay. This is the IO is the whole object. The whole object equal to Ig plus MD square. M is the total mass. D is the Y bar. Then Ig equal to 10.18. Okay. So part B, you look at the whole object. Okay. Okay. Now, if you say, sir, is there any way I find this answer from the appendix? Let's say a question asks you center of mass, center of gravity G of the datum here. We don't know why, but this one is very direct. This one is very direct. So let's say I give you 2 objects. Okay, let's say I give you the normal clock, the old clock with arm and body. So you give you a certain value, so and so. So if you refer to this table, how you find and the reference of interest is at O here, or the center of this here, right? So we refer back to this table. If you're given this object in the test, application problems, right? This is your datum. So on the table there, don't confuse with cylinder and this one, but actually it's the same. So this one, you know that this is a rod. This is a rod, right? So rod, you use the bottom one. So I equal to Ig plus MD square. Rod have its gravity, right? This is the G point, G1. This is G2, G2 for the disc. But if you're referring to O, If you're referring to O, the whole question is IO equal to I this O plus I, not this lah, rod, and this O. So you look at individual. So if this rod will be here, right? So rod is from O to O here. So you refer to this of this chart. Your O is here, right? So you're using Ix prime Y. This one, you use Ix prime. Will give you this one very small. Okay, it will give you 1/3 m r square. Okay. Or if this one change to plate, it depends. If it's a plate, then you use this one. Okay. If the plate, let's say I change to plate. I use rod. Okay. Rod. So rod, I use Ix prime x. So this one is from here. But here, okay, so maybe I extend this one. So this one, I have I rod about O is I G plus M D squared. There's no D there. There's no D. Rod from here, from O. So IG, you read from the table. So you have IXX something. Then here, this also same. This at the center. So you're reading this one from the center. So you're actually looking at z-axis. So go and read at IZZ. Okay. So here you go and I this O equal to I Z Z in the table, which is 1/2 m r square plus md square. There's no d there. There's no d because you are referring to O. Yeah. Now, what happened if the question changed from O to a reference point? I modified this question. If the question asks you point A here, what is the moment inertia at point A? Then you modify this equation. This one you change to A, this one change to A. When you change A, there's a distance already. So for the first rod, you refer to the center of gravity, G1. This is your D1 here. D1 here. Okay. For the second object with the disc, you're referring to from A to the center of gravity 2 here. This is your D2. So there's a D2 here. Plus md square. So the d is d2 square. Understand? So that is the difference between when you change the focus point to somewhere else. It depends when you solve it, how you look at it. Okay. Sorry, from the this. Yeah, because this, how we look at you here, like from here. When you solve this also, we look from here. So this also we look from here. If you look from here, then different already. You look from here, you're using Z, this one already. When you look at the top, this also same. You need to use the same axis already. We read from the top. You look at my marker pen. if you look at the top here, your z-axis is vertical already. Means you use IZZ. For the disk also, you look from the top, you are using x and y already, and not z anymore. It depends on where you look at. You must be consistent for all the bodies. So there's no one exact way of solving it. There are three-dimensional x, y, and z, depend on how you solve it. Yeah. All right. Okay. Okay. So we go a little bit more on the equation of motion, and then we call it a day. Right. Now we assume you already know how to find the IXX, IY, IZZ from the table. Now we want to link into F equal to MA. F equal to MA. Again, your A is stay, but what is different is your mass. You still need to find rho V. So if you look at this diagram, might be complicated, but again, it's still F equal to MA diagram, where there's the rotation of alpha and omega, there's a center of gravity, there's a weight, and so on. All right, everything. Okay, so this one you read lah. At the end, you will be using F equal to MA. The A will be focused on the center of gravity of the objects. Okay. And when you focus on center of gravity, you can switch into x-axis, y-axis, and z-axis if it's three-dimensional problems. Okay. Okay, so this one you read is actually derived from the chapter 5. So we have a rotational motion. So this one is you split all the x into f lah. So this one I go very fast. Okay. So you should be familiar when you look at this one. Is the chapter 2 kinematics diagram, free body diagram equal to kinematic diagram or kinetic diagram. F equal to FA. It's just a transformation into rigid body only. Okay. All the force equal to MA. Okay. All the force equal to MA. Rigid body have rotation, all this. Again, we are looking at A. What is A linked to rotation? A, you have normal and tangent direction. Okay, there's an equation for normal acceleration, tangent acceleration. Okay, linked to omega and alpha, right? So normal direction is AN equal to omega square R, AT equal to alpha R. Still the same. But again, we are repeating F equal to MA diagram. Okay, so this one you read lah. So it's like the cross products and so and so. Again, if you F equal to MA, I will go there very fast. Okay. So here is just to find the X bar, Y bar, usually. X bar, Y bar. I want to show you very fast in one of the question. So this one you read lah. I want to ask you to derive. Important is the application. Okay, we arrive at one equation. Okay, with this one. You need to find the moment at point P. So you have M A, right? F moment, you know moment, right? Force multiplied by distance, right? Still remember moment, force divided by perpendicular distance. So force, MA, right? MA Okay. At the end, what is important? If you want to find a moment at a certain point, reference point, you just need to add one more equation. It is all the moment at the interest point equal to Ig alpha. After all the slides, summarize into, you want to find a moment on the rigid body, you take Ig multiplied by alpha. Acceleration, angular acceleration. Okay, the detailed derivation you can read from the slides. Okay. Okay. Now there are two equations. One is on the top, one is at the bottom. This one, Ig alpha, is that you pull all the interest point into center of gravity. This one, if you are not acting at the center of gravity, you need to find your y bar, x bar, and so on. This is more complete equation, but usually we recommend you to use this approach. You pull all the interest point to center of gravity. Okay. All right. Now, how you find the I, second moment inertia? Again, I equal to Ig plus md square. I equal to Ig plus md square. Where d is the distance to the reference point, right? Distance to the reference point. This is the d, right? How you find this d? This is a rectangular. This r square equal to x square plus y square. Square root, you get this one. Still the same, although there are different notation there. We're still looking at I equal to Ig plus md squared. Yeah. Okay. The rest you read, The rest you read. At the end, you arrive at one equation. The rest you read, Okay. It's a very lengthy derivation. Okay. So again, you have all this but you see all this actually still go back to I equal to Ig md square and mp equal to Ig alpha. This equation. Okay. Now for translation, this one also you read Translation. Translation it means you move in the straight line. When straight line, no rotation. No rotation, alpha 0. So when alpha 0, your moment 0. Yeah. One translation means no rotation. You move in the same orientation. So the mg 0. Okay. Now, when you move in the straight line, again, this diagram is F equal to MA. F equal to MA, still the same. This, what you need to know is that you have a reference line, where is your F acting on, and so on, equal to MA. So you only need to know where is the center of gravity is moving. Okay, F equal to MA. So let's say you have all the force on the left-hand side. MA, you will see that there's a direction of the motion. You just need to find the axis and then find right MAG. That's all. And then there's a D. D means there's a distance of a reference point there. Okay, this D is to tell you to calculate this one. Okay, there's nothing complex, although it looks a lot of notation there. Okay. Okay, so yeah, so in summary, for translation, mg 0, because at the center of gravity, for translation, translation means no rotation in the straight line, the linear, it doesn't rotate. So at moment at the center of gravity 0, And F equal to ma, you have x direction, y direction. Okay, the rest you read. Collinear same, F equal to ma. Recall when you have a collinear, you have tangent and normal direction. That's it. Okay, when you have a collinear motion, you have a normal and tangent direction. Only your F equal to ma, still same, but the acceleration here changed to normal and tangent direction. You focus on the center of gravity now. Okay, center of gravity. Okay, this is when the collinear motion. Okay, so collinear motion of collinear motion, no rotation. So mg 0. Moment, rotation is there's no moment. Okay. This one also you read lah. Okay. So this one is the application in the real case, F equal to ma. This question you can solve in chapter 2 approach, but sometimes the question force you to use chapter 6 question. Right? So here in chapter 2, you're able to solve, but also you can solve using chapter 6 question, F equal to ma. But here, chapter 6, it forces you to go to the center of gravity. Right? Okay, so I go to example 5, then we call it a day. So you look very familiar. This one is chapter 2 question, but it gives you the G center of gravity there. Right? So you can still solve it. Right? Chapter 2, you straight away draw W from G. Then you solve F equal to ma. You know that this one move in the straight line from the right to left. So acceleration here, F equal to ma. Then solve for the unknown. But for example, this one, you need to only call out 3 equations, right? So you're given mass, blah blah blah, friction here. So friction between wheels and the road. Wheels and the road means there's only one friction force and one contact force. If you see wheels and road, give you this one. Wheels means you only have one normal force. If you combine two wheels normal force into one. Yeah. Okay, you draw free body diagram like what you did in chapter 2, but now you focus on central gravity. Do the same. NA and B. No, this one have 2 sorry. Determine acceleration. Oh, okay. The question now, it asks you to focus on one of the wheel. So acceleration is the real driving wheel, so you need 2 contact force. Okay. So if the question didn't ask you about front and the back wheel, just assume one normal force. But if this question, you see this question asks you front and back, so you need 2 contact force. Okay. So you put in the friction force and so on. So why there is no friction force in front? It tell you front wheel are free to rotate. Free rotate means no friction force. Yeah. Free to rotate means no friction force. Okay. Solution 1, you use equation of motion what you learned in your chapter 2. The equation of motion, solution 1. Here, center of gravity, mass, you use moment, F equal to ma, F equal to ma. Moment at G, means you put here, moment at G, how many force do you see? This one, and this one. So this force will create moment. You know moment, right? Force multiplied by perpendicular distance. So this one, clockwise, this one, anti-clockwise, this one, anti-clockwise. So you have 3 moments, NA, NB, FB, multiplied by the distance. So this NA, what is the distance here to here. This one rotate moment. This one rotate moment. This one rotate moment. This is the D. Okay, so equal 0. Equal 0. Why 0? Because this one move in a straight line. Okay. Then this one F equal to ma at a G and so on. You put in all the equation. Okay, now why this is moment equals 0? Because this move in the straight line. The car do not move up, move down. No rotation. The rest you already know, F equal to ma. Okay, the rest you know already. We want to find what is the acceleration at the center of gravity here. This you do not know. This one also you do not know. Okay, so this one in x direction, this one in y direction. You know that the car do not go up. So this one automatic 0. Okay, the rest is substitute. You can find the AG. What else? This is a solution to free body diagram, kinematics. Okay, so this is the first one is the first solution by using this one. Second solution is you have left hand side, right hand side. You use at the point A. You use moment. The first one is 3 equation. Second one you only need to use equation with this moment equation. On the left it start from A. Moment at A equal to the sum of equation in to the A. Give you the answer. So A here, you look at this one. Actually, it's a flip. This actually is a flip. So this one is here. All the moment that you see at this point, right? Point A, right? It asks you point. You can find one point at point A. So when you stop at point A, you see this one, FP don't have moment. I put here, this one C, this one C, this one don't see. Then equal to the sum of all the mass which is here. Okay. How to find moment? MA is a force. MA is a force. You write MAG, draw an arrow, direction of motion. MA is a force. Multiply by the distance here, 0.3. Then you solve for the unknown. You still get the same answer. Yeah. So there are two methods. One is these 3 equations by using at the G location. Second one is you use the same approach, add one more, which is moment at the same one of the point. Okay, both also moment. Moment left equal to moment right. This one is the total overall, which is this side equal to this one. So actually, I should write this one over here, this one over here. But the concept is the same. Moment on the left equal to moment on the right. Okay, we stop here. Go home and see if you have any question. Come and ask me. Okay, so there's a correction there. So we stop at example 5. We continue next week. Okay. Okay, we stop here.